Hey, welcome back, everyone. We're going through 15 more exam-style SnowPro Core questions, one at a time. I'll read the full scenario, walk through every single option out loud, and then give you a beat to actually think before I come back and break down the correct answer, along with why the other choices don't hold up. This particular set leans a little deeper into some real operational territory. Failover behavior, scaling policies, unloading configuration, warehouse internals. These are the questions that trip people up, not because the concepts are hard, but because there's always one option sitting right next to the correct answer that sounds almost right. So let's get into it. Question 1, and we're starting with disaster recovery. Which objects require reconfiguration after failover in Snowflake? This one's a multi-select, so keep an eye out for more than one right answer. Your 5 options: warehouses, schemas, databases, SNS topics, and storage integrations. Take a second and think about which of these actually depend on something outside of Snowflake. All right, the correct answers are SNS topics and storage integrations. Here's the reasoning. Warehouses, schemas, and databases are all objects Snowflake fully manages internally. After failover, a warehouse just gets resumed, a database is already replicated and ready to go, and a schema is just a logical container along for the ride. None of them need a human to go in and manually fix anything. SNS topics and storage integrations are different because they both reach outside of Snowflake into actual cloud infrastructure. An SNS topic is tied to a specific AWS account and region, so after failover, it has to be repointed at new queues and in the new region. And a storage integration depends on a cloud IAM trust relationship that was scoped to the original account. That trust has to be reestablished before the new primary can keep ingesting data. So the real pattern worth remembering here is internal versus external. Anything Snowflake fully owns comes back automatically, and anything that reaches into outside cloud infrastructure needs a human to go update it. Here's why this actually matters in a real incident. Imagine failover happens at 2 in the morning during an actual regional outage, and everyone's scrambling to confirm the business is back up. Databases and warehouses will just work, which is a relief. But if nobody remembers to update that storage integration's IAM trust, ingestion pipelines will silently stop pulling in new data, and nobody may notice for hours because the queries against existing data still run fine. That's the kind of gap a well-run DR runbook has to explicitly call out. Otherwise, "we failed over successfully" quietly turns into "we failed over successfully and stopped ingesting new data." Moving to question 2, and this is about performance tuning without touching your SQL. Which feature is most appropriate for reducing scan cost without modifying SQL queries? Your 4 options: clustering keys, search optimization service, query acceleration service, and materialized views. Think about which one of these actually works completely behind the scenes. The answer is search optimization service. Once you enable it on a table, it quietly builds and maintains its own access path in the background, and your existing queries just start benefiting. Nothing about the SQL itself has to change. Now, why not the others? Clustering keys genuinely help scan efficiency too, but somebody has to choose the right key and think through how the data should be organized, which is a real design decision, not something transparent. Query acceleration service is a legitimate performance booster, but it works at the execution layer, offloading pieces of an eligible query. It doesn't actually reduce how much data gets scanned in the first place. And materialized views require you to explicitly create a new object and then write or rewrite queries to actually take advantage of it. So that's the opposite of transparent. When the requirement specifically says no SQL changes, Search Optimization Service is the one built exactly for that constraint. You might be wondering why that no SQL changes constraint even matters in practice. But think about a large organization with hundreds of existing dashboards and reports already in production. Rewriting queries or redesigning clustering across all of that is a massive, risky undertaking. Being able to flip a switch on a table and have selective point lookups get faster without touching a single downstream report is a genuinely huge operational win, which is exactly the scenario Search Optimization Service was built to solve. Question 3, and this one's about Snowpipe. Which statement about Snowpipe load ordering is correct? Your options: timestamp-based enforcement, strict global ordering, single-threaded loading, and best effort sequencing. Give it some thought. How do you think Snowpipe actually handles order when it's ingesting at scale? The answer is best effort sequencing. Snowpipe generally tries to process older files before newer ones, but that's a tendency, not a guarantee, because ingestion happens in parallel across multiple files. Two files can absolutely land out of order under the right conditions. So why not the others? Timestamp-based enforcement isn't a thing Snowpipe does. It doesn't read or enforce anything based on timestamps embedded in your data. That logic has to live in your own downstream design. Strict global ordering just isn't realistic, given how parallel ingestion works. Relying on load order as a guarantee would be unsafe. And single-threaded loading would badly hurt throughput at scale, which is the opposite of what Snowpipe is built for. So the practical takeaway, if your downstream logic actually needs a reliable sequence, don't lean on ingestion timing. Build explicit timestamps or sequence numbers into your data instead. Picture a real pipeline where this bites someone. Say you're ingesting change data capture events for a customer's account balance, and two files land almost simultaneously due to parallel ingestion. If your downstream logic naively assumed last loaded equals most recent, you could end up applying an older balance update after a newer one, silently corrupting your data. That's exactly why seasoned Snowflake engineers bake a sequence number or event timestamp into the payload itself, so correctness never depends on ingestion timing at all. Question 4, and this one's a bit more technical. 2 correct answers here, so pay attention. Which 2 Snowflake virtual warehouse clauses can specify compute generation in a create warehouse SQL statement? Your 5 options: generation clause, warehouse size clause, resource constraint clause, warehouse type clause, and query policy clause. Take a moment. This one requires knowing some fairly specific DDL syntax. The correct answers are the generation clause and the resource constraint clause. Here's what's going on. Generation is the newer, simplified way to set a warehouse's compute generation, accepting a plain value like 1 or 2 right in your create warehouse statement. Resource constraint is the older original mechanism, using more verbose constants like standard Gen 1 or standard Gen 2, and it's still fully supported for backward compatibility alongside the newer syntax. Now, why not the rest? Warehouse size controls compute scale, x small through 6x large, which is a completely different dimension from which hardware generation the warehouse is running on. Warehouse type picks between standard and Snowpark optimized architecture families, which again is a different decision entirely from generation within that family. And query policy isn't a real clause at all. It doesn't exist anywhere in Snowflake's warehouse DDL. This is genuinely useful to know in practice because plenty of existing infrastructure code out there still uses the older resource constraint syntax, so you'll run into both. And here's a practical nugget worth holding on to. Gen 2 standard warehouses generally offer better price performance than Gen 1 for the same size, so this isn't just syntax trivia, it's an actual lever for squeezing more performance out of the same warehouse size. If you're doing a cost review and notice a fleet of warehouses still sitting on Gen 1 with no resource constraint or generation clause specified at all, that's often a quick, low-risk win worth investigating. Question 5, and this one's a quick fact check. Which file format is used by default for Snowflake data unloading compression? Your options: bzip2, zstandard, gzip, and brotli. Think about which of these Snowflake reaches for automatically. The answer is gzip. When you unload data and don't explicitly specify a compression option, gzip is what Snowflake applies. It's a well understood, broadly compatible format that balances compression ratio against speed reasonably well, which is exactly why it makes a sensible default. bzip2, zstandard, and brotli are all legitimate options you can request explicitly, each with its own trade-offs in compression strength versus overhead, but none of them are what kicks in automatically. Knowing the actual default matters more than it sounds because it affects what file extension and decompression tooling your downstream consumers should be expecting if nobody bothered to set compression explicitly in the first place. Here's the real difference worth remembering when you're actually building a pipeline. The moment you're handing off unloaded files to a downstream system that expects a specific format, don't just assume gzip and move on. Some legacy tools or partner systems expect uncompressed files or specifically want a different codec for their own ingestion process. And mismatched expectations here are a classic source of why is this file failing to load tickets that eat up more time than they should. It sounds like a small thing until you're the one debugging it at 9 at night, tracing a failed load back 3 systems to discover someone forgot to tell the receiving pipeline that the export was gzip compressed by default. A 5-second check of the copy into statements compression setting upfront saves that entire debugging session later. Question 6, and we're talking data architecture patterns now. Which Snowflake features are used in a medallion architecture transformation layer? Multi-select, so more than one answer here. Your 5 options: transient tables, permanent tables, dynamic tables, stages, and materialized views. Think about which of these actually belong in the middle layer of a layered pipeline. The correct answers are transient tables, dynamic tables, and materialized views. Let's talk through why. Transient tables are a common choice for intermediate transformation stages because they skip the extra storage overhead of failsafe while still supporting normal ETL staging work. Dynamic tables are built specifically to automate incremental transformations, refreshing themselves as source data changes, which makes them a natural fit for a transformation layer that would otherwise need hand-built orchestration. And materialized views genuinely earn their place too, pre-computing and storing aggregate results for performance-sensitive, repeated queries inside that transformation stage. Now, permanent tables typically hold down the final, curated layer of a medallion pipeline rather than the messy intermediate work. They're built for long-term persistence, not staging. And stages exist purely to hold raw files for loading data in, which puts them in the ingestion layer, not the transformation layer at all. So the skill being tested here is really about matching each object to the correct layer of the pipeline. And here's a design habit worth adopting from this. Before you create a single table in a new pipeline, it genuinely helps to sketch out which medallion layer it belongs to and pick the object type that matches that layer's actual job, instead of defaulting to permanent tables everywhere out of habit. Teams that skip this step often end up with bloated storage costs from fail-safe retention on tables that were only ever meant to be scratch space for a transformation step. Question 7. Back to fundamentals. Which Snowflake object represents an MPP compute cluster? Your options: virtual warehouse, database, stage, schema. You probably know this one, but let's confirm it. The answer is virtual warehouse. That's literally what it is, a massively parallel processing cluster made up of multiple compute nodes working together to execute queries and DML. Databases and schemas are purely logical constructs for organizing objects. Neither one runs a single query without a warehouse actually attached to do the work. And a stage is just a storage location for files with zero processing capability of its own. This separation between storage, metadata, and compute is one of the defining architectural ideas behind the entire platform. And understanding that the warehouse specifically is the compute piece underlies nearly everything else you'll see on this exam. It's worth sitting with just how deliberate this separation is too. Because storage, compute, and metadata are all decoupled from each other, you can spin up 5 completely different warehouses of different sizes, all pointed at the exact same database, with zero contention between them. One team's massive reporting job doesn't slow down another team's quick lookup query, because they're running on entirely separate compute clusters, even though they're reading the exact same underlying data. That's the practical payoff of understanding this architecture, not just the exam answer. Question 8, and this is one of Snowflake's signature features. Which Snowflake feature allows instant copy of a table without duplicating storage initially? Your options: time travel, materialized view, zero copy cloning, external table. Think it through. The answer is zero copy cloning. Clone a database, schema, or table, and Snowflake creates the new object by referencing the exact same underlying micropartitions the source already has. Storage only actually starts accumulating once one side or the other diverges through real changes. That's what makes cloning nearly instant no matter how massive the source object is. Now, why not the others? Time travel is about querying a table's past states for recovery. It doesn't create a new independent object at all. It's about looking backward, not duplicating forward. Materialized views store pre-computed results to speed up reads, which is a completely different job than cloning. And external tables just reference files sitting in outside cloud storage. They have no internal cloning mechanism whatsoever. They aren't a copy construct in any sense. This efficiency is exactly why zero-copy cloning has become such a standard move for spinning up dev, test, or backup environments in seconds instead of hours. Say you're a developer who needs to test a risky schema migration against a full copy of production data. Without zero-copy cloning, that might mean requesting a multi-terabyte export, waiting hours, and burning a ton of storage just to get a sandbox. With cloning, you run one command, get an identical environment in seconds, and only pay for storage once you actually start making changes that diverge from the source. That single feature genuinely changes how teams approach testing and experimentation on Snowflake. Question 9, a shorter one about unloading. Which option controls whether Snowflake writes one output file during unloading? Your options: single, partition by, compression, max file size. Think about which of these is specifically about file count. The answer is single. Set it to true, and Snowflake consolidates everything into exactly one output file instead of the multiple files it writes in parallel by default. Partition by is about something else entirely, organizing unloaded data into a folder structure based on column values, not collapsing anything into one file. Compression only affects how the data gets encoded on disk, no bearing on file count at all. And max file size caps how large any individual file can grow, which can influence file count indirectly, but it doesn't guarantee a single file the way single explicitly does. Using single trades away some unload parallelism and performance in exchange for a simpler file that's easier for legacy downstream systems to consume. A real trade-off worth understanding, not just a trivia fact. Here's where you'd actually reach for this in the real world. Imagine handing off a file to a legacy vendor system that can only ingest one flat file per batch, no exceptions. Without single, Snowflake would hand you a folder full of split files by default, and you'd need extra tooling just to stitch them back together before the vendor could even accept the data. Setting single to true skips that whole extra step at the cost of losing some parallelism on the unload itself. It's worth pairing this mentally with max file size too, since they represent opposite philosophies for the same underlying problem. Single says, I don't care about parallelism, give me one file, period. Max file size says, let Snowflake split things up for performance, just don't let any one piece get too unwieldy. Knowing which philosophy a given downstream system actually needs is the real-world decision behind picking one setting over the other. Question 10, and this is the big scenario question, so bear with me while I read the whole thing. During an Enterprise Edition audit, a Snowflake DBA discovers that a critical production multi-cluster warehouse running in autoscale mode has its scaling policy set to economy. Business users are reporting intermittent query delays during mid-morning peaks. The DBA wants to minimize queuing during these peaks while accepting slightly higher credit usage. What scaling policy change should the DBA apply? Here are your four options. Option 1, decrease min cluster count to reduce baseline credit consumption. Option 2, change the scaling policy from economy to standard. Option 3, switch the warehouse to maximized mode to eliminate scaling delays. Option 4, increase max cluster count without changing the scaling policy. That's a lot to weigh. Take your time. The answer is option 2, changing the scaling policy from economy to standard. Here's the full picture. The economy scaling policy is deliberately conservative. It waits until it estimates roughly 6 minutes of sustained queuing before it starts a new cluster, which is great for keeping credit usage tight, but it also means real users feel that delay whenever there's a genuine demand spike. Standard policy flips that trade-off around. It starts additional clusters proactively as soon as queuing shows up or a shortfall looks likely, which is exactly the behavior needed to cut down on those mid-morning peak delays. Now, why not the others? Decreasing min cluster count actually makes things worse, not better. It lowers the baseline, sure, but that means scaling now has to climb from an even lower starting point when demand spikes, which increases lag rather than reducing it. Maximized mode does eliminate scaling delay entirely, since every cluster just runs all the time, but that blows past slightly higher credit usage into a much bigger unnecessary jump. And increasing max cluster count without touching the scaling policy doesn't actually fix anything, because economy's cautious triggering logic stays exactly the same regardless of how high the ceiling is set. You just have more clusters available that still take just as long to actually start. Standard scaling policy is the precise, proportionate fix this scenario is asking for. And this is honestly a great example of how the exam likes to test judgment, not just recall. Every wrong option here isn't obviously wrong. Decreasing min cluster count sounds like a reasonable cost lever. Increasing max cluster count sounds like it should help with scaling. And maximized mode genuinely does solve the delay. The skill being tested is recognizing which lever actually controls the specific behavior described, how proactively new clusters start, versus levers that just adjust cost or capacity without touching that timing at all. It's also worth thinking about what happens after this fix goes in, because that's where the slightly higher credit usage trade-off actually shows up. With standard policy, clusters will now spin up a little earlier and a little more often than they did under economy, including for some spikes that might have resolved on their own without a new cluster. That's the cost the business is explicitly agreeing to eat in exchange for happier users during peak hours. And honestly, that's the kind of trade-off conversation a good DBA should be having with stakeholders directly, not just quietly flipping a setting and hoping nobody asks about the credit bill next month. And that habit generalizes well beyond this one question. Practically every performance or cost decision in Snowflake ends up being some version of this same conversation, trading a bit more spend for a bit less friction, or vice versa. Getting comfortable naming that trade-off out loud, instead of treating it as a hidden side effect of a technical setting, is honestly a big part of what separates a junior engineer clicking through settings from someone who's actually operating the platform with real judgment. Question 11. Back to warehouse basics. What happens to running queries when a warehouse is resized? Your options. They are canceled and restarted, they immediately use the new size, they continue unaffected, or the warehouse must be suspended. Think about how disruptive you'd expect a resize to actually be. The answer is they continue unaffected. A resize doesn't touch anything that's already executing. Queries in progress keep running on the original compute resources until they finish naturally, while only new queries that start afterward pick up the new size. So why not the others? Canceling and restarting running queries would be needlessly disruptive, and that's simply not how Snowflake behaves. Immediately use the new size is wrong too, because that would mean interrupting active work mid-execution, which again isn't what happens. Only future queries get the new size. And there's no requirement to suspend the warehouse first either. Resizing is designed to work cleanly on a warehouse that's actively running. This non-disruptive behavior is exactly what makes resizing such a practical lever for real-time cost and performance tuning. You can scale a warehouse up ahead of an anticipated heavy workload or back down once it's over without breaking anything currently in flight. This is actually one of those features that feels almost unremarkable until you compare it to older database systems, where resizing compute often meant real downtime or at least disrupted sessions. Being able to say, we're expecting a huge batch job at 2 a.m., let's bump this warehouse up right before it starts and back down right after, without any coordination or maintenance window, is a genuinely underrated piece of operational flexibility that teams lean on constantly once they realize it's there. Question 12, and we're back in disaster recovery territory. Which Snowflake object becomes read-only in secondary accounts before failover promotion? Your options: warehouses, users, stages, secondary databases. Think about which of these is actually a data object with a formal read-write state. The answer is secondary databases. They're explicitly kept read-only by design in Snowflake's replication model, right up until a failover promotes them to primary. That's the exact mechanism that guarantees only one side of a replicated pair can ever accept writes at a time. Why not the others? Warehouses in a secondary account are just suspended compute resources, not data objects with any kind of read-write state at all. Users get replicated for identity consistency, but they aren't data containers that go through a promoted versus not distinction. And stages hold files, but they don't carry that same formal read-only semantics that a replicated database explicitly does. This single writer guarantee is exactly what prevents a split-brain scenario where both the primary and a secondary might somehow accept conflicting writes at the same time. It's a core piece of how Snowflake's replication architecture stays consistent under the hood. Think about why this guarantee actually matters operationally. Imagine two teams, one at the primary region and one at the secondary, both accidentally trying to write to what they each believe is their active database during a network partition. Without the enforced read-only state on the secondary, you'd risk two divergent versions of the same data existing simultaneously, with no clean way to reconcile them afterward. Enforcing read-only until an explicit promotion event removes that entire failure mode by design. Question 13, and this is a multi-select about external tables. Which features apply to external tables? Your 5 options: manual refresh option, micro-partition pruning, read-only access, schema on read, fail-safe support. Think about what makes external tables fundamentally different from native ones. The correct answers are manual refresh option, read-only access, and schema on read. Here's why. External tables can be refreshed manually with alter external table refresh, which updates the metadata to reflect files that changed in the external location, a step that's genuinely common in real setups. They're strictly read-only, since the actual data lives and is managed entirely outside of Snowflake, so DML through Snowflake just isn't possible. And they follow a schema on read model, interpreting the structure of the data at query time rather than enforcing it up front, which is a core distinction from how native tables behave. Now, why not the rest? Micro-partition pruning doesn't apply because external tables don't use Snowflake's native micro-partitions at all. Pruning instead relies on file and row group level metadata. And failsafe support doesn't apply either, since failsafe is a protection mechanism scoped only to storage files Snowflake actually owns and manages, and external data simply isn't that. Recognizing which native capabilities external tables lose out on is a recurring theme across architecture and performance questions on this exam. Say your team is deciding whether to load a massive external dataset into native Snowflake storage or just query it in place as an external table. Knowing that you'll lose micro-partition pruning and fail-safe protection is a real factor in that decision. If that data gets queried constantly and needs strong pruning performance, native storage might genuinely be worth the extra cost, whereas an infrequently touched archive is a perfectly reasonable candidate to leave as an external table. There's a cost angle here too that's easy to overlook. Leaving data as an external table means you're not paying Snowflake storage costs for it at all, since it physically lives in your own cloud storage bucket the whole time. That can make external tables an attractive middle ground for genuinely huge data sets that get queried occasionally, but don't justify the cost of a full native copy, as long as the team is comfortable with the read-only constraint and the lack of fail-safe protection that come with that choice. Question 14, sticking with search optimization, which predicates are supported by Snowflake search optimization for structured data? Again, multi-select, your 5 options: substring predicates, schema creation, equality predicates, range predicates, delete operations. Think about which of these are actually query predicates in the first place. The correct answers are substring predicates, equality predicates, and range predicates. Substring search is supported, improving like and contain style lookups through token-based indexing, though it does come with a minimum length constraint worth remembering. Equality lookups on structured paths are a core use case too, enabling fast point lookups instead of scanning across every micropartition. And range-based filtering on numeric or date fields, say, also benefits, improving pruning efficiency for that kind of query. Now, schema creation and delete operations don't belong on this list at all, and for the same underlying reason, search optimization is entirely about accelerating how queries find data, and neither of those is a query predicate. Schema creation is a DDL operation, and deletion is a DML operation, completely different categories of work. Knowing exactly which predicate types are in scope and which operations don't even apply is what separates a precise understanding of this feature from a vague one. And here's the connective thread between question 2 and this one, worth noticing. Both questions are really about the same feature, search optimization service, just tested from 2 different angles. One tests when to reach for it, the other tests exactly what kinds of queries it actually speeds up once you've turned it on. Seeing that connection is a good habit in general. A lot of exam questions aren't testing isolated facts, they're testing the same underlying feature from multiple directions. And question 15, our last one, another unloading question. Which Snowflake feature controls maximum output file size during unloading? Your options: partition by, single, max file size, compression. Last one, think it through. The answer is max file size. It directly governs how large each output file is allowed to grow during an unload, giving you a lever to balance file size against parallelism for whatever's consuming the data downstream. Single solves a different problem entirely, forcing everything into one file regardless of size, rather than capping the size of potentially many files. Partition by is about logical folder organization, nothing to do with size control. And compression can shrink file size as a side effect of how the data gets encoded, but it isn't the setting actually built to enforce a size cap. Tuning max file size thoughtfully is a genuinely common piece of real-world performance work too, since files that are either too large or too small can both create bottlenecks for whatever reads them next. Say you're feeding unloaded files into a downstream system that processes each file with a fixed amount of memory. Hand it a single enormous file with no size cap, and you can blow past what that system can handle in one pass. Setting a reasonable max file size keeps every individual file within a predictable, manageable range, while Snowflake still handles splitting the output across as many files as it needs behind the scenes. And that's all 15. Let me run through a quick recap, because this set covered a lot of ground that's genuinely useful beyond just the exam. Question 1. After failover, only externally dependent objects like SNS topics and storage integrations need manual reconfiguration, while Snowflake managed objects come back automatically. Question 2. Search optimization service reduces scan cost with 0 SQL changes required, unlike clustering US or materialized views, which all demand some form of design work. Question 3. Snowpipe offers best effort sequencing, not a strict ordering guarantee, so downstream logic needs its own timestamps or sequence numbers if order matters. Question 4. Generation and resource constraint are the two valid clauses for specifying warehouse compute generation, one modern and one legacy. Question 5. gzip is the default unload compression format. Question 6. Transient tables, dynamic tables, and materialized views belong in a medallion architecture's transformation layer, while permanent tables and stages sit in other layers entirely. Question 7. A virtual warehouse is Snowflake's MPP compute cluster. Question 8. Zero-copy cloning gives you an instant table copy without duplicating storage up front. Question 9. Single forces unload output into exactly one file. Question 10. Standard scaling policy is the fix for reducing peak time queuing on an economy-configured multi-cluster warehouse. Question 11. Resizing a warehouse never disrupts already running queries. Question 12. Secondary databases stay read-only until failover promotion. Question 13. External tables support manual refresh, are read-only, and follow schema on read, but skip micropartition pruning and failsafe. Question 14. Search optimization accelerates substring, equality, and range predicates specifically. And question 15, max file size is what actually caps output file size during unloading. If it helped, go ahead and drop a like. It really does help this content reach more people working toward the same certification. Subscribe if you want more of these rounds, because there's a lot more ground still to cover. And if there's a specific area you want the next set to focus on, replication sharing, resource monitors, whatever's giving you trouble, drop it in the comments and I'll build the next round around it. Good luck with the exam, keep at it, and I'll see you in the next one. And hey, one very last thing before I let you go. If any of these 15 felt shaky the first time through, that's completely normal. Go back, replay the ones that tripped you up, and actually say the reasoning out loud to yourself before you check whether you got it right. That one habit, explaining the why in your own words instead of just recognizing the right answer when you see it, is what actually turns into confidence on exam day.